This is the Pinacol rearrangement that I did. Here's our reactants and our acid catalyst. The acid will grab onto the OH, and the H will join the OH, and the bond between the O and the H will move on to the O and form water. And since the oxygen lost a bond, it's now positive. And in order to fix that and stabilize it more, the bond between the O and the C is going to move up and form another water. And then now that this lost a bond and electron, it's not as stable anymore. So in order to stabilize it, the bond from over here is going to move over to where this positive charge was, and now it's stable. But now since this bond left, this over here is now unstable since it lost an electron. It's now positive. So in order to fix that, one of the lone pairs from the oxygen is going to come down and form a double bond. They'll resonate down and form a double bond, and the positive charge will go away. And now these are resonance structures, and since this moved over here, if you skip this one and go to this one, the oxygen is now positive because the O lost the electrons through resonance. And the water that we had in the beginning will come and join this OH, and what you'll see here is this structure. And the water turned into H3O and is now a catalyst, and it'll grab the hydrogen and the oxygen, and this bond will resonate down here, and then you have our product and our water as the final products. Here is the energy diagram that I predicted. Since I predicted that delta G was negative, the reactants are lower than the products. Here are our intermediates and the three transition states that I predicted. This transition state, I believe, comes from when the H3O attacks to the OH, and then the energy catalyst is lifted up again in transition state 3 when the H2O turns into H3O plus and is another catalyst in our reaction. An example of recent use for a Pinacol rearrangement was in an article that I found called Mechanistic Insights into Chiral Phosphoric Acid Catalyzed Asymmetric Pinacol Rearrangement, which was published in 2018 by 3 experimenters. The reaction was catalyzed by chiral phosphoric acid and resulted in high levels of enantioselectivity, and the study used the density functional theory to investigate the mechanism and origins of stereoselectivity between different catalysts. In the end, the study found that a strong CH to O bond in the transition state, you can see in TS1 major, was found to contribute to higher levels of enantioselectivity, whereas bulkier catalysts did not bring the higher levels.